Okay.
Shall I share the screen? How?
Yes. So the first thing, just to inform to all the assistants that we are recording this session according with the rules of the European Commission, European Innovation, so European Sustainable Energy Week. Okay, because this webinar must be accessible to all the people that has been participating during this event. And from our side, I give the floor to the chairman of the project SUSTENET, and Dr. Filipe Neves. The floor is yours.
Okay, thank you, Raul. Hello, everyone. Welcome. It's nice to be here with all of you. So I will give you an introduction to the SUSTENET initiative, okay? And then we will follow up with the program and the agenda that you can see here. Okay, we have Hao from technology, Hao from AEInnova, Dan from Ionic, Ivana from FlexiRamics, and Frederic from Thermal Power System. So I hope you enjoyed the program of today. So this is the second webinar that is organized within the SUSTENET action. It is the first one that is organized within working group 3, okay? And as Raul mentioned, this event is hosted under the umbrella of Sustainable Energy Days also. So let's move to, so my name is Filipe Neves, okay? I am chair of the SUSTENET Cost Action. I am a researcher at the National Laboratory of Energy and Geology in Lisbon, Portugal. So a very brief information about cost action. So SUSTENET means, it entitles for Sustainable Thermoelectrics European Network. It is a cost action. And what is a cost action? So a cost action essentially provides networking opportunities, not only for researchers, but also for innovators, in order to strengthen European capacity to address many challenges in terms of scientific, technological, and societal challenges. So here it is highlighted the main networking activities that can be performed within cost actions. So there are what is called events like meetings, training schools, mobility of research and innovators through short-term scientific missions or through virtual mobility. And also, it also give grants for presentation at external conference to the members of the cost actions. So regarding SUSTENET, we intend to deep more into the thermoelectrical technology topic. And the main objective is to develop a sustainable large implementation of thermoelectric technology within Europe. And we will cover many different topics that will go from material sustainability, performance and cost, standardization, which is very important, also circular economy, market expansion, and also stakeholder engagement. There are research objectives and capacity building objectives. So I highlight here some of them in terms of research objectives. I highlight like promote innovation and sustainability, identification of key challenges related with supply chains, for example, environmental aspects. Also regarding the topic of finding more sustainable thermoelectrical materials, define and standardize properties measurement protocols, identify most promising thermoelectrical application, and so on. Regarding capacity building objectives, highlight, for example, the engagement of young researchers and innovators, and also the maximization of the interdisciplinary collaboration to promote knowledge exchange and access to research within the different organizations in Europe, and not only in Europe, okay? So the SUSTENET action, it is organized in 4 working groups. One more dedicated to research of more sustainable thermoelectric materials, which is working group 1, that is titled Scaling Sustainable Through Artificial Intelligence. Then working group 2, it's dedicated to application and user cases. Working group 3 to business development and supply chain. And finally, we have a working group dedicated to dissemination and communication and training activities. So if you are interested to join, if you don't did that yet, you can join by clicking through this link. You will have access to this web page, and then just click apply to join the working group that you seem more interesting to work within. You can follow our activities on the website of SUSTENET and also through the LinkedIn page. So, and that's all the information that I wanted to share with you about the SUSTENET Cost Action. So today we are adding a webinar organized by the working group 3 leaders, Hao Yin from technology and Raul Aragonés from AEInnova. So I pass the floor to Hao. You can go ahead, and thank you all.
Thank you,
I will
Filipe.
stop sharing my screen because, yeah, okay.
Thank you, Filipe. And hello, everyone. I can see many familiar names, but also someone that we have never met before. So a few words about me, myself, and the company Technology. So I came to Denmark 2008 to pursue my PhD in nanomaterials. And then we got some patents on thermoelectric materials, which is the fundament of a company Technology, which was spin out from a university. I joined the company as the first engineer, and then gradually became the CTO and now the CEO and the biggest owner. Worth mentioning is at the end of last year, we have expanded our business into Asia. So now we are a truly global company, working exclusively on the design and the manufacturing of thermoelectric modules. As you can see, I was educated and trained as an engineer, but learned how to run a business in thermoelectrics. I don't have any slides today for this webinar, because I don't think what I'm going to talk is difficult to understand. I don't need any slides to support my arguments. So here comes the first information that I really want to spread out, is I'm very optimistic to the future of thermoelectrics. For me, thermoelectric carries all the characteristics as the solar panels did 30 years ago, right? Try to imagine back to 2090s, when solar panel was just started, right? At that time, the only applications was the tiny window on this pocket calculator, right? If at that time people tell you that solar panel is going to be one of the major primary energy source, you wouldn't believe in it, right? But only in these 3 decades, which is very short in history, solar panel becomes so big scale. So it's very interesting to think about what happened at that time. It's equally interesting to think about thermoelectrics right now. Actually, it's at the edge of being implemented in large scale. And I have no doubt in that, because think about what thermoelectrics have is almost the same as what solar panels had at that time. You know, what we need is energy input, largely available energy input, which is waste heat. As we all know, that waste heat from industry exceeds the total amount of all the renewable energies combined, right? All this industrial waste heat that we got from burning fossil fuels, we're wasting large amount of it. So those energy, in most of the time, it's there. Whether we use it or not, it's just there, right? So solar panel started to explode doesn't because the sun started to shine, right? The sun has been shining for millions of years. And And people start to think, okay, what if we can harvest a small portion of those sunlight, which is there? The same goes to thermoelectrics. The waste heat is there. What we need to do is to start using it. And many people saying, okay, thermoelectric has a very low efficiency. It doesn't make sense. It's not completely true. Think about automotives, right? People will go for this 1%, even 0.5% of the increase of the efficiency in combustion engines. And those 0.5% or 1% requires millions of investment into the development. But for thermoelectrics, we haven't had that investment from industry yet. And this shouldn't be the excuse. So the relatively low efficiency shouldn't be the excuse of not trying to implement this technology into real applications. If we say, now the heat is there, it's free, let's assume the heat is free for application. And then we have a technology to convert that heat into electricity. And then what the question next is, how do we implement it? How do we design the system so it's profitable, so it's cheap enough to produce energy? And from that point of view, we are at a very good time, a very good time in history, because now we have the tailwind of recycle the waste heat, of upgrade the waste heat. As many of you already know that the European Union has dedicated course for upgrading waste heat from industry. And that meant to be for thermoelectrics. So I'm not saying basic research is not important. It's by all means very, very important. By increasing the performance of the materials, by having more abundant and non-rare element-based materials, and also a scalable manufacturing process, we will make this energy more attractive. But doesn't mean that there's no commercial future for existing materials. What we need is to find, if not design, a use case which we can use the existing materials and the existing manufacturing methods. Everyone has seen these ceramic modules that we can buy on the market for decades, right? For half a century that we can buy this. But the thing is, it has not changed much since 50 years ago when NASA has designed this to put it on a deep space probe to convert heat from radioactive materials in the deep space. At that time, when NASA designed this, it is a perfect design for deep space use. But is it a good design for industrial use? Probably not. Many people have tried to use this in industry and then figure out, first of all, the price is way too high. And this module, if you buy it from qualified providers with a guaranteed quantity or property and quality, it's not cheap, right? It's 20, 30 euros each. And buying more of them will not give you much discount because this one contains tellurium and ceramic substrates. And the manufacturing method is not meant for mass production. Because this one, which is 4 by 4 centimeters, contains about 12 by 12, so hundreds of legs. If we're going to cover 1 square meter of areas, and then we're going to need about 1,000 or hundreds of modules like this, which contains millions of legs. And how do we produce and cut all those legs and make them into modules with this ceramics that might crack in installation or during heat and cooling cycles? I have been wondering why thermoelectric modules have to have that, and I've been asking around. The answer is it has always been like this, right? So for technology, well, we really try to identify real use case by existing technologies. The biggest challenge that we have identified is these modules are simply not meant for industrial use. They're too expensive and too difficult to scale. As thermoelectric generators, when the efficiency is low, and in order to generate enough power, we need large areas. That means we need to cover a huge area to generate useful amount of electricity. We're talking about square meters, tens of square meters, even hundreds of square meters. So we need to think about how do we meet their need, this need. And therefore, we have came into this design where we don't use ceramic substrates. This is based on polymers. And then we can make it bendable in both directions. When it's bendable, it has much less internal stress. And when we don't have ceramics, we break the limit of the size. So in principle, or actually in practice, we can produce very large single thermoelectric modules. Many people have seen that I've shown A4 sized single thermoelectric modules. So in the future, we're going to produce thermoelectric modules in continuous manner, and then we cut it into desirable sizes. We believe that that opens the opportunity to implement thermoelectrics into real industrial cases. When I say industrial cases, I mean, for example, the heat exchangers, where you can easily have tens of square meters of heat exchange areas in a very compact heat exchanger. We're also talking about cover entire roof of a building, where we utilize the indoor and outdoor temperature difference. We're also talking about wearable devices, where we use human body as the heat source. There, we also need flexible modules. Talking about the raw materials, we all know that tellurium is produced in very few countries in the world. That means if you're still relying on tellurium, that we are relying on vulnerable supply chains. The project that Filipe and me and some of you in the audience have worked called START project. We try to integrate non-tellurium based materials into large-scale thermoelectric applications. The project has come to an end with promising results. Now we can produce thermoelectric modules with tetrahedride and magnesium antimonide. So we have excluded tellurium in the module fabrication. So you can say, to some extent, we are very ready to go larger scale. And then what we need to know is to tell the entire world, the entire industry, that please reconsider thermoelectrics. It's not the same technology that you have known for decades ago. Now we can implement this into your application, but we cannot avoid that people still put us into the old mindset that people say, okay, how do we compare thermoelectrics with the grid, with the electricity they can get from the grid? Or how do I compare the price of a thermoelectric generator or cooler or a thermoelectric generator with the batteries, right? So the thing is, we need to break that mindset. For many sectors, industrial sectors, the amount of electricity is one thing, but more important is we give them an excuse, we give them a storytelling resources to think, okay, now they can recycle the waste heat they have generated. For example, the data center, right? So AI and big data, that's probably the hottest topic in the world. But the energy consumption of data center has become a bottleneck. For the data center operators, they have to wait, at least in Europe, they have to wait years before they get a approval to build new data centers. for them, if we give them a good argument that now they can increase their energy efficiency by a few percent by implementing thermoelectrics, that equals that we give them a ticket to jump the queue in front of the others because they have a higher efficiency of using their energy. It doesn't matter if it's 1% or 10%. Of course, if 10% will be perfect, but every percent counts. So that's the first signal that I want to spread out. So tell the people who knew or who haven't heard about thermoelectrics, now thermoelectrics is in the picture. Consider it in the smaller scale where we can power autonomous sensors as long as there's a small heat source or cold source, right? Then we can generate electricity on site, on demand, without batteries, without cables. It doesn't matter how much electricity we generate. It matters that now you can run your device, can be sensors or can be anything else, in the place where that's not possible to generate electricity. Someone asked, there's a screen share. No, I'm not sharing any screens. I'm just talking. For smaller scale, then for large scales, right? Think about those areas that you have low-grade waste heat. It can be the surface heat from a huge annealing oven or a chimney or flue gas pipes, where you easily have tens of square meters of hot areas, right? So we can generate some electricity. So the second information that I'm aware of the time, I want to spread out is thermoelectrics. If we're going for scale, we need to think about the supply, the security of the supply chain. As any industrial sector, manufacturing sectors, thermoelectrics is depending or will depend on the global supply chain. And actually, we already suffer from the global supply chain. The existing modules based on tellurium, we're not getting materials from Russia, and we have more and more challenges getting them from China. And those two countries contribute for over 80% of the supply of this. So as the European companies, what shall we do? And also, when we have the raw materials, we need to find out how to produce them. With the cost of manufacturing in Europe, it makes us very difficult to compete globally. And technology, we have tried to outsource some of our non-critical processes. And then we got in touch with sub-supply in East Europe. They promised that they can match the price of the Chinese suppliers, but then they end up being three times more expensive. And they said, sorry, they promised, but they just couldn't do it better. Right. So as a European, of course, we have a better welfare, we have a better environment, which we all benefit from it. But from manufacturing point of view, we're competing globally. How do we secure our supply? And maybe many people think, arguing that we need to de-risk, decouple from certain countries. The thing is, as a startup company, I've seen so many high-tech startups, right? They have the state-of-the-art technology. They have the most interruptive technology in the world. But they are handing their recipe, they're handing their secrets over to the suppliers in Asia because they can manufacture, they can realize this design into products, right? It's not like people are stealing our IPs. It's we are finding the suppliers which are cheaper and better. It's a natural flow of information and knowledge. We cannot cut it. Compared to block the flow of goods or information and knowledge, the more we need to think about, okay, how do we maximize what we're good at in Europe and make use of the global resources? And globalization cannot be reversed. We cannot live in our own bubble assuming that we can survive and keep our social welfare without relying on the global collaboration. With that I want to conclude my talk in this webinar. That in this webinar, we have invited people or the companies who are not the traditional or conventional players in thermoelectrics. And that's on purpose. Because thermoelectrics has been blamed to be in the niche market for long enough. We need to invite people who are not experts in thermoelectrics, but experts in their fields. In this interdisciplinary areas where thermoelectrics and other innovative technologies, when they meet, new ideas is generated, a new application is identified. And that opens a broader future for thermoelectrics. And my name is Hao. I come from technology. Thank you very much.
Thank you very much, Hao, for your contribution to this webinar and for this long vision that could be the essence of Europe. So working together to achieve the best thermoelectric materials with the lowest price and have big scale, not only for powering subsystems or small devices, but also for improving the energy efficiency of processes with big scale thermoelectric. So from my side, let me right now share my screen. I am Raúl Aragonés. I'm the next speaker. Okay. I think it's now being shared. It's not sharing the screen, so let me again share the screen, full screen, should be easier. Okay. So in my case, I will also give a special thanks to the European Commission that has given us this opportunity to present this webinar inside the European Sustainable Energy Week. You know that this is an initiative of the European Commission to engage all the players that are related to energy efficiency to participate in several events. In this case, the events are focused on the EU Sustainable Energy Days that lasts all the month of June. But also there is an event that is present 1 week in Brussels, where all the companies that are in this movement of energy efficiency could have a space to speak, also to showcase their innovations in the European Sustainable Energy Fair that is also related to this event. In our case, alternative energy innovations will present what is the evolution of the usage of these TEGs that Hao manufactures into final application that solve particular use cases in the industry. Right? We'll showcase several use cases, and we will focus in one that is a very highly demanded applications for improving the energy efficiency of steam processes. I am Raúl Aragonés, the main founder of Alternative Energy Innovations, the CEO of AEInnova. And just to make a very short intro of AEInnova, it is a bit like how it's a spin-off of the microelectronics department of the Autonomous University of Barcelona. We were awarded by the European Commission European Innovation Award, Radar Awards in 2024 with the most sustainable technology in Europe. That means the thermoelectric is a real value for the industrial digitalization. The company is invested by the European Innovation Fund, the EEC Fund, and also the European Innovation and the EIT InnoEnergy, the biggest clean tech accelerator in the world. We have several patents, several of them granted, and others that in patent pending. Company basically composed by 19 high qualifying engineers and personnel, and and with projects practically worldwide. We have projects of heat power sensors from Latin America, North America, Asia, and Africa. Also, I want to clarify that this company is the final result of several European research and innovation projects, mainly funded by the European Commission, CINE Agency, and also AEISME Agency. Again, also like ERANET, Eureka, Eurostars. So all of these players has given us the opportunity to launch from a promising idea in 2014 to what right now it's a commercial product, certified product, commercial product that can be purchased in these markets. So as my colleague Hao said, there is a big amount of energy that is lost in industrial processes. Particularly, the fifth part of the European energy needs are lost in form of waste heat. So it's a big energy that is completely useless, that is emitted to the atmosphere. And AEInnova, what has been doing during these 10 last years, has been identifying how we can use this energy to power quotidian, so usual, let me say, bottlenecks of the industry. And we've identified that really the European industry has several challenges to become more, in one hand, more competitive with other promising new markets, to become more energy efficient and more sustainable. And all of them are related to improve their industrial processes. In one side, to become more productive, you need basically to reduce your downtimes and breakdowns. And this can be usually served if we are able to detect how their machines are working. Passing from corrective maintenance, that means you're fixing your machine when it breaks, to proactive maintenance. That means you're able to determine where your machine is going down, and you can predict the potential issue of the machine, and you can anticipate the breakdown of the machine. Also, to improve your energy efficiency, you can basically identify where are you leaking the energy. In this case, the steam. Big steam processes like big oil refineries has thousands, dozens of thousands of steam traps where they lose steam in their steam traps. But also when we are focused on big steel making plants with big furnaces, they have big energy inefficient furnaces that they want to monitor, have a better monitor of their heat processes to improve their energy control of the assets and improve the production of the quality of the production, and also the energy losses on these big steel making plants, and also cement rotative kilns. When these companies look for industrial devices, they couldn't find in the hand those that are wired with big challenges due to the cost of wiring. Only have sense commonly in really critical assets. But when they want to monitor not critical assets like auxiliary pumps, mixers, ventilators, they commonly try to move to wireless devices because they need less investment in infrastructure, mainly moving data around the plant, but they have a big bottleneck due to dependence of the lithium battery. Commonly, industrial sensors are being powered by not rechargeable lithium battery. This the main business of our competitors, because they want to keep you with a recurrent expenses, recurrent capex of an OPEX, just replacing every few years the battery. And this is a very good business for them, but it's a bad business for the environment, because every day they are moving to the containers millions and millions of useless lithium battery that has a very bad environmental impact from the harvesting of the raw materials, lithium, from the triangle of lithium. For just 1 kilogram of lithium, we need one ton of raw materials of lithium, salts of lithium, but also cobalt in the Congo and Zambia. They need 1 ton of rocks of cobalt to obtain 1 kilogram of cobalt. Then move this to South Africa, move this with vessels to China, and then manufacture in China lithium batteries that then they are charged with an electric mix of China that is mainly coal, and then move again this battery to Europe. So these are a dramatic carbon footprint that we need to face globally. And this is where, in this industry, has sense to take benefit of the heat of the processes to have a self-power industrial, because also when you install this sensor in heat industries, the heat affects the lifetime of these devices. So the solution is battery-less and take benefit of the heat of the process. Easy, better integration, better long-lasting. Again, we have a continuous energy source, so you can send data very far. And this, again, a very important bottleneck from traditional wireless sensors. Today, we have been speaking with several customers that are commonly using wireless HARP protocol that has few meters of distance in communication, and they need to invest hundreds of thousands of euros just to have a correct network of repeaters inside a big facility. Hundreds of repeaters that cost everyone 2,000, 3,000 of euros per every wireless repeater. When with long-range wireless like LoRaWAN protocol, that is an open protocol, with just one gateway that costs 1,000 euros, you could cover all the full facility. So this is really a challenging innovation, thanks of using not battery power sensors. Also, are more flexible. Also, lithium battery is explosive, so there is a lack of portfolio of sensors because lithium is explosive, and commonly you cannot install this type of sensors in oil and gas refineries, chemical plants, but also food industry. So just the floor of wet is explosive. You cannot use this also in soybean manufacturing plants. So these are big bottleneck again due to the explosive areas. What AEInnova has created is a certified for explosive industries, heat power, battery-less, maintenance-free, long-range wireless that has full edge computing capabilities inside the device. So we solve all the problems, all the challenges of these industries with one solution of sensors. In one hand, we have three main pillars. Energy harvesters. I purchased to my colleague Hao Thermoelectrics that we assemble in the Thermoelectric device. This module with just 25 degrees Celsius of delta between the hot surface and the cold surface, we generate until half a watt of power. And this device to give electricity to our family of battery-less long-range sensors. We have three main sensors: vibration to real-time vibration, monitoring in relative machines, motors, compressors, pumps, mixers. The in-due extreme temperature sense for monitoring up to 8 thermocouples in high temperature facilities and high temperature furnaces for steel making plants, aluminum making plants, also rotative kilns for the cement plants, and finally to attack steam leaks and steam traps with ultrasound detection. And last but not least, data travels to my cloud platform, Neves, our visualizer, or to a customer HMI platform, where they can be easily integrated to any type of cloud in premises or just our cloud. Thermoelectric, so with just heat, we can generate clean energy that can be injected to my network of sensors up to 300 degrees Celsius that supports this Thermoelectric. The right one is the bigger that has more energy to power at the same time up to 3 sensors. The left one, the Thermoelectric that can power just one sensor. And also these devices could power any third parties vibration sensors from our competitors. So, for example, IFM, Endesa, Emerson, they could power these wireless sensors using our Thermoelectrics. Then the family of industrial IoT devices for three mainly applications: vibration, stimuli detection, and high temperatures. Initially, with LoRaWAN, that is this a free long-range network communication protocol, but also narrowband IoT, that is one protocol that incorporates SIM card and doesn't need any type of wireless infrastructure, just uses the 3G, 4G network. So 3 main applications. This for vibration monitoring, one heat power that can generate energy for up to 3 vibration sensors, 3-axis vibration sensor, 6 kilohertz of bandwidth to have a full diagnostic of the potential malfunction of the machine, from vibration failing that generates data from cavitation, lack of lubrication, unbalancing. So any time of potential malfunction can be detected. In my right, a gas power plant in this area where we are monitoring vibrations in these engines, and below, what can our customers see in our cloud platform, where they can identify, depending on level of criticality, green, yellow, and red. You know how is the danger of the machine. And in the right, you just apply the window of the spectrum, and you can identify where the energy is located. You identify what is the origin of the malfunction of this equipment. Second, that is the main introduction of this webinar, is about steam leak detection. It's a way of doing steam processes more energy efficient and let them save millions of euros per year in form of steam leakages, because steam traps is a device that detects water condensate in the steam pipelines and evacuate this water condensate to the boiler. If this water is traveling around kilometers of a steam trap, can create water hammers that can make the pipeline of steam explode. This is why they need to move to evacuate this water condensate, and the equipment is called steam trap. So this device set over the steam trap is able to detect by temperature comparison in the inlet and outlet of the steam trap, but also listening the acoustics, the sound of the steam trap, what is happening inside of the steam processes. So this is a first generation, first test in 2021. So Thermoelectrics plus the IoT in the same device. First modeling to obtain the performance of this energy harvester. First modules, first test in the laboratory, and first test in our thermoelectric generator laboratory. Then to test in one oil refinery plant in the left, and in the right, in one big stakeholder in pharma. Okay, so this is the LoRaWAN gateway from our partner Kerling that has 2 kilometers of radius of communication and up to 10,000 sensors at the same time with just only one gateway. And this is the equipment that monitors 2 temperatures, inlet and outlet, and also listens the steam trap. The same approach here. So this is a buoy steam trap. This is a thermodynamic steam trap. So inlet and outlet temperature, and this microphone, ultrasonic microphone, that listens inside the steam trap. And then the equipment evolution to a new generation that was most compact. Again, 2 temperatures and ultrasound. This was from 2022 to 2024. So a most compact device. We reduced more than 70% the overall size of the thermoelectric, and also the overall size of the IoT device. So again, monitoring 2 temperatures, inlet and outlet, and ultrasound. This equipment was not really industrialized in a scale. This is why we moved to the last version, that is what right now it's commercial, and we have first projects running on Latin America, and also in just the next month in the Middle East. So this is the equipment, thermoelectric by one side, because sometimes the energy is not near to the steam trap. The ultrasonic and temperature detector, the steam leak detection, that you locate over the steam process. And these are example of one of our customers, in this case, Petrobras in Brazil, the biggest Latin American oil company. We just set the thermoelectric in the steam pipeline. We set the system to detect, in this case, temperatures. This equipment is called TempSense. We're launching in next month the device LeakSense that also incorporates ultrasound, and then the inlet and the outlet of the steam trap. And we monitor temperatures. We determine when the equipment is losing the steam. But also, there's a food industry of the steam trap. We're also testing and detecting ultrasounds plus temperatures. This name is Colacao, the Idilia Foods. It makes cocoa chocolate powder. So we detect temperatures and ultrasounds. These are validation previously to install in Petrobras. And what our customer sees is inlet and outlet temperature that allow us to detect when we are accumulating steam water in the inner part of the steam trap. Also ultrasounds that detect the level of sounds inside the steam trap and the counts per minute that opens and closes the steam trap, indicating to you that this device is working properly. Last but not least, an equipment to monitor temperatures in big furnaces to determine gradients in temperature. This is an example of one customer in Morocco, ArcelorMittal. We detect different gradients of temperature using this equipment that has 8 thermocouples. And in general, we are addressing a big challenge in all the industries. So food, oil and gas, chemical, iron and steel, pharma, paper, cement and concrete, and petrochemical. We produce the devices up to 200 units per month here in AEInnova. We have all the machines to produce all the devices. And also we have a subcontractor here in Barcelona where we can produce up to 2,000 devices per month. So in general, we're ready to make exportations in all the continents. Technology that we have the know-how here in Europe and from Europe to the world. Several patents in Canada, US, and Europe. The AEX and the IFX certification global for expulsion processes, and several compliances to sell technology in markets like Japan, Europe, America, and coming now Anatel in the next weeks for Latin America, for Brazil. And this is my contact. Thanks for sharing with me these minutes, and I give the turn to the next speaker. So thanks. If you're finally, we will give 5-10 minutes for Q&A. Okay. Thank you for your time and your interest. Thanks, Ivana. So I think the next speaker is Ivana or Dan. I don't remember. I don't have the agenda. Okay, Dan, your turn. The floor is yours.
Thank you very much. Thank you very much. And we'll also share my screen here. Hang on a second. So, hi everyone. My name is Dan Verja, and I would like to present something we call the From Reactive Maintenance to Smart Infrastructure. First of all, thank you, Filipe, for opening this session. And I noted one important keyword: unlock new markets. That's very important, of course, and I will contribute to that part as well. Thank you also, Raul, for the last session here as well, where you mentioned use to waste it. How you mentioned it as well in a good way. We have a lot of waste in the world. Let's use it smart. Leak detection was mentioned. We mentioned dangerous goods from lithium batteries. And let me just onboard you in how we got in contact with the Thermoelectric systems. There's a guy, I call him the Heat Buster. His name is Jörg Reder, working at Technology. He contacted me back in 2023, mentioned this Thermoelectric system, and I thought, wow, this is interesting. Let's start to speak together. Now we are 2026, and I will onboard you today, dear audience, in something we call manhole applications in the district heating area. However, let's see here, next picture. My name is Dan Verja, working as commercial manager at Vionic. Vionic is a supplier, European supplier with headquarters in Sweden. I'm from Sweden, as you can see, the Swedish flag, but also do have colleagues in Netherlands in the Dutch headquarters as well. So we have 2 headquarters, one in Sweden, Borås, one in Apeldoorn in Netherlands. And we are specialized in digitalizing the distribution network in the energy market, most likely the district heating market, and also the water, drinking water and sewage water area. So let's bring it on. Digital manhole monitoring. You all have taken your steps on something we call the lid in the street. And that lid could be actually a lid into a district heating manhole or chamber. Back in the days, 1970s, it was a big boom in Europe to build a lot of district heating networks. Personally, I think that's not that very old. I'm myself born 1979, so I still feel myself pretty young. But when you start counting 70th, yeah, we're actually approaching 50 years at the moment. And this is exactly the same scenario we can see in this presentation. On the picture, we have two good examples of installations, one in the area close to Stockholm and the second one in the area close to Vienna in Austria. The main challenge we can see in the utilities here in Europe. The infrastructure, as I mentioned, the 70th has been some years ago, so it's still aging year by year, and we would like to have it in use for many more years. We can't simply replace it all in 1 year. We all know the climate changes, the climate challenges. It's either very sunny or could be very, very rainy. In the end, that mixture, rain, the only process that loves rain, besides the farmers, of course, is corrosion. In a chamber under your footstep, there is a chamber with a lot of steel, and the corrosion actually loves that kind of moisture. But moisture means something will be destroyed over time, and that means even higher operational costs. And as we all do, we need to be careful about our resources. So that's why the sustainability requirements, they will not decrease, they will for sure increase for the future. So that's why digitalization is not longer optional. It's the real foundation for the future here. So let's open a lid in the street. And if you're allowed to open a lid in the street, you might see something like this. It's a concrete chamber, typical design back in the 70s, because that was back in the days the only way to build a district heating network. You had a steel pipe, you had buried it in concrete, and you needed to have a lot of manholes. What we have seen today here is that there are about 700,000 of these manholes chambers still in use in Europe. 700,000. So just imagine if we don't take care about them, we have a big problem in the infrastructure. This picture is a good example. It might be a very nice, cool picture on a remote distance. This is actually boiling green district heating water once the pipe could burst in such a network or in the manhole. As you can imagine, it's still a nice picture on a remote distance, but don't be showering in that water because that might be your last shower in your life. The challenge again, we know that the heavy rain will affect the system of flooding. There could be leakages, there are leakages in the system as well. And mentioned before here, the working conditions must be secured because you don't shower it more than once. That's a simple fact. And of course, we would like to boil the water that's needed to be boiled, and otherwise we waste simply energy resources. So let's keep the system as tight as possible. Of course, on a bigger picture, we have this green transition, decarbonization that we all speak about, and that simply requires better operational intelligence. We need to know what is underneath our feet. And sustainability is the key. We need to know what is underneath our feet to bring the best sustainability. So the big why then, how the operators work today. It's a lot of reactive maintenance. Once you see something leaking, you solve it, of course. The customers, the utilities, try to be one step ahead. So of course they do a lot of manual inspections, if they ever have the time for it, of course. But in general, there are a lot of reactive maintenance. That's the is situation we would like to see, and we all need to reach level of continuous monitoring and be ahead of the disasters by having predictive maintenance. And all that is based on a data-driven decision. So we need to get data from the system. And this is now where we actually step by step get closer to the Thermoelectric technology. Further onboarding, a manhole like this, the chamber looks like this, as you can see on the picture. By having water level information, by having temperature, is this rainwater? Is it district heating water? You see the humidity increases. That's a sign of something is leaking over time. There could be someone unauthorized opening the lid. You are not supposed to live down there. It's really, really deadly. And you need to know where is the overflow. It's not on purpose to keep these chambers forever, but utilities need to have some sort of information on what they should prioritize. What chamber should be removed next year, over the next year. And this is again not done in a day or year or decade. This will take decades to fix, of course. So by having this fast response time, by having an industrial IoT device inside the chamber, we can, first of all, increase the worker safety. We will use our resources in a great way, and in the end, create a better environment. Simple as that. So, thank you, Hao, from technology and your team, helping us with this energy harvester that we call the WEHM1. It's an energy harvester utilizing the delta T in our case of 30 degrees. That's what we say should be the minimum. We can go lower than that, but by having 30 degrees delta T, we can, as well as Raul presented in his earlier presentation, have sensors installed out there. In our case, we installed them in manholes, and these sensors communicate by 4G or NB-IoT. We have this real-time communication. We get the data to the cloud. We can have a clever, great alarm management, and as well we can see the trend analysis. By having the trend in our hands in the data, we can do the clever decisions. Some very fresh examples, one from Austria, one from Sweden. It typically looks like this. We have the not that much corroded pipes in the end, but we have the harvester installed on the hot surface, what we call the flow pipe. We secure that we have the 30 degrees from the flow pipe. Normally you have 95, even more degrees on the flow pipe. The chamber typically has about 25 degrees, so we always have a good delta T of minimum 30 degrees. That will serve our sensor, in this case, this manual application, where we actually add all the sensors that can help us, support us with the level, temperature, moisture, etc. So in the end, we have three main benefits. Operational, we will reduce the emergency callouts, be ahead of the disaster. It will help the utility and the customer to prioritize what chamber is the most affected one, what should be prioritized for the next year. The maintenance planning, of course, is a final output of that one. Environmentally, we are the leak busters in this industry. So by having pinpointing where we have the leak in chamber, we can get in the early stage. You don't need to manually inspect these chambers, running around or traveling around with the car, opening lid by lid and see dry, wet. Well, we need to do something. And that's the strategic final one as well. Predictive maintenance. So collect data for clever decisions, and we can promote this digital transformation to get the real digital twins in the smart cities. As well, you cannot optimize what you cannot see. So we are actually the eyes down there underneath your feet, the lid that you can find in the street. Business case, as Hao mentioned as well, this is a kind of free of charge energy that we see it. It's the waste heat. Instead of having the use of lithium-ion batteries, first of all, it's classified as dangerous goods. It's dangerous. So just the transport nowadays, not for free at all, to transport lithium-ion batteries. That's one cost. You need to remember that. The manholes are typically positioned in the street. If you should open a lid, you need to stop the traffic. It's a big effect on the society. Security-wise, you should be 2 people. They have for sure some sort of hourly cost. Of course, different all over Europe, but there is a cost, and you can easily plan 2 hours of breakdown. Since it's a dangerous area, you need to have some sort of emergency evacuation tools or safety equipment, simply spoken. Batteries, they don't last forever. In our case, typically 3 to 5 years. So, and then you have to dispose them somewhere. So the environmental impact is there. Just seeing a typical usage of 10 years up to 3 cycles of this step-by-step is the must. You install them, you replace them the first time, you replace them the second time. So just imagine that all these costs together are far higher than the cost of installation of the harvester. So unlock the new market. Yes, we have unlocked the new market, I would say, Filipe. There are out there about 700,000 of manholes, and this is a great example of how we can use the already in place heat, what we call waste heat, where we can drive and get the energy to the sensors. On a bigger picture, this is of course one thing that will promote the climate resilience, the smart cities, sustainable infrastructure, and in the end, their efficient resource usage. And the last part, we need to lower the energy consumption, and this is of course one good thing to promote that finding. Of course, less leakages, less water losses. We don't need to focus on boil too much, of course, fewer emissions. And in the end, it's about to keep the infrastructure in place as long as possible. It's not on purpose to replace a pipe every 50 years or so. If you can use it longer, use it longer. Focus on what is important. That's the part. So a final quote from Bionic and me, Don Varia. The green transition is not only about producing energy differently, it's about to operate infrastructure smarter. So thank you everyone for listening to my contribution, and we are open to collect all the questions in the seminar by the end. Thank you very much.
Thank you very much. So I think the next invited is Ivana.
It's me, yes.
Okay, Ivana, thanks for joining. Your turn.
So yeah, I think you can see the screen.
Yes, perfectly.
So good afternoon to all, and thanks for joining the seminar, the webinar, and thanks to the organizer that I was able to participate and explain or give a little bit of idea what we do. So my name is Ivana Ivanovic. I'm working as a commercial manager at FlexiRamics in the Netherlands, and here to shortly discuss how our flexible ceramics technology also plays a role in the new generation of thermoelectrics. In a value chain, I'm much earlier, we are much earlier than the previous applications, but that's what makes this webinar so interesting as well. So, should we move? Yeah. So previous participants explained this and how I started with it, how much of the energy is today processed but also lost as heat, no matter the different industries mentioned here and the pressure they are on to recover at least part of that waste heat, where thermoelectric generators come into place as an option to convert part of this wasted energy into electricity. For that, they should be reliable. So that, of course, I use some of the schematics, so hopefully, at least as a scheme, it is correct. The TEGs operate under extreme conditions, so you can say in a steep temperature gradients, they have chemical exposure, and there is a problem of the reduced efficiency and the reliability, especially with the material interfaces as they are degrading over time. So this is often or very often limited cause of the material interface degradation. What do we do? So FlexiRamics is making pure ceramic microfiber non-woven. I also have a very short film to show how it looks. Basically, it looks like a Kleenex tissue paper, but made of ceramics. So it has a ceramic performance. It has a polymer-like flexibility, and that is something which is unique. Of course, as ceramics, it has a high temperature stability, and it is still lightweighted, so that's easy processable. So this combination makes it interesting for different applications, one of which new architectures in thermoelectric generators. I think so this is simple how it looks. So this is ceramics. It doesn't burn, it's flexible, it's very thin and lightweighted. That is what we make. If you think about the technology, it's a solid gel, the proprietary technology we have. It goes through the different temperature gradients and then comes as a continuous non-woven fiber out of the oven. This product is then further treated or converted into composites, coatings, impregnated structures that gives versatile options for the applications. And when we talk about the electronics, energy, you see the application electronics, catalysis, batteries, also in insulation, electrical, and even such as material infiltration. So for what makes our material powerful or interesting, and talking about new materials or advanced materials, is that one material platform actually addresses multiple engineering challenges. So we can talk about the lower thermal expansion, which gives dimensional stability, so the CT is close to copper. We can talk about the faster heat dissipation, especially in a lateral XY direction compared to the overall used glass cloth. It has 4 times better thermal conductivity. It shows 70% less of the signal loss when used the same as just mentioned glass loss in a 6G or other systems. And the last but not least, it has that more efficient energy recovery or a waste heat recovery. So that is where we find the place also in the new architectures of thermoelectric generators. Oops, sorry, wrong button. I wanted to move the slide, so I pressed stop sharing. So back on. So why our material, FlexiRamics material for thermoelectric generators? It has a multiple functions. So it can be used as a reinforcement layer. It does provide structural support. It improves the thermal interface and offers electrical insulation. And the last but not least, can be used with the different protective layers as for chemical resistance. value proposition, when we talk about then flexible ceramics that FlexiRamics makes for thermoelectric generators, would be in that CT matching, which provides then a better reliability. It has this slight, when it is in a composite, as we make it for this application, it has this slightly conformable interface contact, so then actually reduces the contact resistance. And coming to the lightweighted, it is very thin, 60 micron, 80 micron, so that it's not compromising, it's still having a structural integrity, but maybe a sort of better design freedom or lightweighted options. So that is, yeah, it looks exactly like that thing that the TEG, the small TEGs, the prototype that Hao was holding at the start. So that is that base or yeah, reinforced film, which can potentially be integrated in tech. How does it look in real life? So we developed this reinforced film, so that what you see is resin reinforced with our flexible ceramics. On this reinforced film, you can still print. You can print functional inks, and then integrated in TEG modules, as showed at the picture. And that this creates then flexible ceramics platform that supports the next generation TEG module design. And just shortly about, yeah, part of the sustainability, of course, as all that already mentioned, more efficient conversion of heat, longer lasting materials because durability or efficiency and reliability will be longer. It has that lightweighted use, so also low material use, and shows or gives also potential for reuse and a different making of the materials that are currently used. What we do with the cluster, so very excited to be part of the cluster and that regional ecosystem that focuses on sustainable innovation. And what we can offer is that advanced materials, strong material science and scalability. We also have this pilot scale capability here in the Netherlands, where we also manufacture the material, and we of course welcome all the collaboration with partners on whether material integration, testing or prototyping. So with that, I just wanted to thank for your attention, and if you would like to explore any projects or technical discussions or questions, you can freely contact us on through this info shown on the screen. So thank you very much.
Okay, thank you, Ivana. I think we can move to Frederic. Just remember that you can write your questions on the chat, and then we have time for discussion. Okay, thank you.
Can you see my screen?
Yes.
Okay, here we go. So I'm going to talk about my company, which is called Thermopower Systems. And we are working on tellurium-free thermoelectric generators, trying to manufacture thermoelectric modules which are totally free from tellurium. And of course, oh yeah, that's the last slide. Sorry, I go back to the first. Yes, let's go here. Right. Yeah, so it's I've prepared this with my colleague Geoffrey Roy, whom I think you know very well. I mean, he's quite known in the community. He's been participating in many such events. So of course, there are many materials, thermoelectric materials. Of course, thermoelectric effect is something that's no one has even invented. I mean, it's an intrinsic property of some materials. And there are many materials that are thermoelectric with different performances and different challenges that are going with them in terms of manufacturing. Okay, so but I will focus on one material specifically today. So just a few words on our company. So we are a Belgian startup. We were incorporated in 2023. So we are actually not a spin-off of the University of Louvain, but we are collaborating very closely with Professor Pascal Jacques, who was the supervisor of Geoffrey Roy. And they've been developing thermoelectric materials using conventional and powder metallurgy since, I think, 2011, 2012. So we have more than 10 to 15 years of research on these materials. And our role as a startup is to industrialize and bring the research to the market. The main target in terms of materials is the iron vanadium aluminum alloy, which is indeed thermoelectric, which can be synthesized with P-type properties or N-type properties. I must say that we are also, as a company, also investigating other materials than this one for different ranges of temperature. But I will focus mainly on iron, vanadium, aluminum today. So our goal is, of course, I will show you what are the challenges, but our main goal is to be able to support all the applications that we have seen today. So you have heard different companies today, and they all develop applications mainly for, I would say, remote and batteryless sensing applications. And if you see the figures of AEInnova, they say, okay, we can manufacture up to 2,000 units, several thousands of units per month. It means potentially you have several thousands of modules to be manufactured per month. If you sum all the companies involved in doing such IoT applications using thermoelectric generators, you can sum up to tens of thousands of modules per month. So if we have to buy this off the shelf from, let's say, the bismuth telluride manufacturers, it, of course, by the numbers, it's less expensive as if you just buy one of them, but it can be very expensive. And also, we think it's not sustainable to use bismuth telluride because simply of the limited quantity available and the tension on the market for this material, and also the supply chain vulnerability. So these are the main things to know about thermopower. So, of course, you have seen different applications today. Most of them, I think, were related to, let's say, Internet of Things. So we are looking at modules to generate electricity with low power. So we need a limited number of modules per application, maybe just one. And you need maybe microwatts, milliwatts, maybe a couple of watts to operate your sensing device and
I think we missed Frederic. Let me think he can join again. This is a problem of the laptop that are not batteryless. Depends in the battery. Let me wait a couple of minutes. There is a problem with the connection.
Probably we can move to some of the questions that
Correct.
are already in the chat.
Yes, we could. If we would like to make any questions from the first speakers, you could write in the chat.
So there are one from Johannes. I don't know if you want to.
Okay. How high is the thermal conductivity of the flexible ceramics?
Yeah, that's probably for me. So we speak about XY, so lateral, and then in PI, so in polymer, I mean compared to the conventional glass used is 4 times higher, so 2 to 2.2 watt meter Kelvin. So we don't talk about, I mean, I'm not comparing the Z direction. So yes, I know I saw the table that was in the chat, but not sure if it is X, Y, or Z. So we talk here about the lateral, so that improves the heat dissipation and the hotspots. And that one is 4 times so higher than glass. So I said 2 to 2.2.
Thanks, Ivana.
I just want to supplement. It's not only the thermal conductivity, it's also thickness, right? Which plays a very, very important role.
Correct. Yeah.
And it's
Frederic,
flexible.
we can't
Most
hear
important, it's flexible. We love flexibility.
Oh. So Johanna's question, very good question. Despite SV is not rare and it's not listed as critical raw materials in the EU, China is producing the majority of SV of the world. Can remember the percentage, but higher number.
Oh no, that's sorry. That's my reply to Johannes.
Okay.
Who asked how critical do you regard antimony as component in thermoelectric materials? I can elaborate more. So antimony has become more and more important. It seems to be the replacement for tellurium in thermoelectrics, and indeed, antimony is much more common. It is produced, I don't remember how many millions of tons per year. But if you look at the origin of this material, we are more dependent on China. At the moment, antimony is not listed as a critical raw material, but as a matter of fact, I mean, we are depending on less supplier. So whether it is a problem or not, I mean, it's hard to say. But before it's a problem, it becomes a problem for thermoelectric, it will probably become a more severe problem for other industries who use a lot of antimony.
And the next question.
But yeah, this advantage is that we need to think the material, where do they come from, and how robust and how secure of the supply of the material.
Also, how for
Hello.
you?
Okay,
Frederic.
I'm back. Do you hear me now?
Yes, perfectly.
Okay, let me start. Let me start again. I just lost the connection. I could see you. I saw the chat.
Perfect. So you can again
All right.
your screen. Perfect.
Go ahead. So I was there. So we are looking at two extremities of target here. So small sensor that must be used without batteries, and then we are also looking at massive waste heat recovery. So trying to use thermoelectric generators for, let's say, up to more than 30 kilowatts. So Hao discussed earlier that we could apply thermoelectric modules on large surfaces. This is exactly what we want to do. Okay. So just a word on the market. So these are generic figures that I got from market research. And there is one very important assumption behind these figures, is that the growth of the market for thermoelectric generation is based on the fact that there is no manufacturing or technology breakthrough. So it's based on the progression that we have seen over the last few years. But if companies like ours and other companies in this session come with breakthroughs and enable large manufacturing capabilities, I think the growth of the market is much larger. So that's a message, and I think this message goes hand in hand with the message from technology. Okay. Now, this has been said already. Actually, the wasted heat is actually the largest unused source of energy. Basically, if you look at the picture on the left, you take all the energy consumption in the EU. What you see on the lower left, you have two kind of reddish or Bordeaux, I would say circle sections. They represent the fraction of energy which is totally lost. So it's 5 to 10% of total European energy consumption, which is completely lost. So as we said, this is a fantastic opportunity to reuse it. Okay, and so as Hao said also earlier, we must rethink the position of thermoelectricity in this against this opportunity in all the different markets that you see on the right. So all the industrial markets, but also the energy production markets are actually concerned. So we have a solution for all these markets. And of course, depending on the quality of the heat, so if it's a low temperature or a high temperature, you will need different materials, obviously. So why are we working on this material? So iron, vanadium, aluminum. One of the main reasons is that these are the most abundant metals.
Sorry, Frederic. The slides are not moving. The slides.
They are not moving.
No.
So I'm not. Do you see it now? I just went out of the.
Yes.
Yeah. Let me continue like this. So you saw the slide on the market when I said market share. Maybe not.
No.
Doesn't matter.
No.
So, okay, so why iron, vanadium, aluminum? So first, it's a very abundant, we have very abundant metals, but also, you know, vanadium also can be available as a pure metal, but usually we buy it pre-alloyed with iron because it's available as an entrant in iron metallurgy. So in Europe, vanadium is also readily available when pre-alloyed with iron. We have no problem of sourcing the materials. It's a reliable supply chain. So as we said earlier, if you take tellurium, that's a problem. It's manufactured mainly in China, maybe also in other countries, but it's a limited quantity, and also it's a vulnerable supply chain. And then this material can also be processed through conventional and powder metallurgy. And then if you think about thermoelectric modules, this material naturally passivates, so it's naturally protected against corrosion, oxidation. And also we don't need like protective barriers against diffusion when we assemble it. So this is another advantage which I didn't mention here, but you see this is an excellent candidate for industrial scale-up. So that's one of our main let's say advantages, or main advantages of the material. Now, of course, what goes along with this is it's a low-cost material. So it's much cheaper. It's let's say 50 times to 100 times cheaper than right. It has no toxicity when we have. Do you still hear me? Yes, okay, because I hear some strange noise from Teams, like if you lost me. So it can be operated up to 400 degrees C. It has a large power factor, actually very competitive. Its major drawback, I would say, is that the efficiency itself, often measured in terms of ZT for thermoelectric materials, is 0.15. So it's a low efficiency. So which means we will have a low conversion efficiency. But another advantage is that we have performed life cycle analysis of this material for certain applications, and we could show that it's actually very competitive and has a big advantage. It's very positive in terms of the different indicators of the life cycle analysis against renewable sources of energy like wind electricity. Same against photovoltaic panels. So this energy, thermoelectric-based electricity will be cheap and will be very interesting and very sustainable compared with other renewable energy sources. So for us, it's a very cost-effective candidate for both massive waste heat recovery and Internet of Things, I would say powering of sensors. So that's how we see this scenario. So where are we, what are we doing now at ThermoPower? So we started with the material, we improved the performance of the material up to ZT 0.15. And as I said, one of the main challenges is to be able to manufacture it up to 1,000 modules per day. So we start, what I'm going to show here is basically the manufacturing chain. And I'm going to say, okay, what are the main advantages and the challenges? So advantages against challenges. So you see here that there's a color code. When it's green, it means we already achieved more than 1,000 modules per day. So doesn't mean we manufacture 1,000 modules in one day, but the throughput that we are observing is above 10,000 modules per day. When it's orange, it means we are between 100 and 1,000 modules per day. So we still have challenges. So now if we start from raw materials, what is particular to our approach is the fact that we have to work with large quantities of industrial raw materials. If you look at research articles or let's say academic researchers, usually the quantities are very low and the modules are prepared from pure materials. We work from raw materials, means you have impurities and we have to compensate for that. Okay. Then if we go to casting, we have revamped a vacuum induction melting oven. We have revamped an oven which allows us to manufacture 20 kilograms of materials batch at a time, which is a very good quantity regarding our objectives of throughput. But the point is that casting requires, let's say, very accurate compensation, for instance, for evaporation of aluminum. Then, of course, we manufacture powders. What is the best is to work with spherical powders for flowability and robustness of the sintering process, compaction, I would say compaction and then sintering process. We work with non-spherical powders because it's much cheaper. So we need to pay attention on how we dispense the powder in the next step of sintering. So in terms of sintering, of course, the most, let's say, widespread technology is spark plasma sintering. So we use this. I mean, it can have other names depending on the company. We develop the things so that we don't have to post-treat the surfaces. So post-machine them or post-surface them. It means we can dice them right away after the sintering. Where we have still development to make, and we are working with partners for that, is we must manufacturing larger discs and also stack different discs. So these are technologies that have been developed by other companies, like stacking discs, but we need to go even larger discs to achieve 10,000 modules per day. Then the dicing is a big challenge, because like conventional dicing approaches like electron discharge machining or let's say conventional saw cuts, they can be very slow because our material is very brittle. So it can be as slow as 2 millimeters per minute, but we could achieve an equivalent cutting speed of 24 millimeters per minute, and we really minimize the kerf loss. Because you know, when you manufacture small thermoelectric legs of, let's say, 1.5 millimeters by 1.5 by 2 millimeters, or even smaller than that, if you lose half of the material, it's really bad. So we really minimize kerf loss here with the hybrid process. Here with dicing, there is no solution. If you want to achieve 1,000 modules per day, we need to process dicing in parallel with multiple machines. And then regarding the assembly, so this is brazing in this case, we have been able to achieve very short cycles and avoid to have vacuum. Of course, avoiding vacuum, having short cycles is very good for our material, but might not be convenient for other materials. But this is our manufacturing chain as is. So we have other challenges. So as I said, this is the manufacturing chain challenge. But of course, we want to build applications. So because we want to prove and go above TRL 6 or 7, or reach TRL 7, I would say. So we have developed a number of tools, and we are working on different applications. We have developed a design tool, which is really an end-to-end simulation tool that solves the thermal and electrical problems, that computes like the exchange coefficients, and that can compute, that can do parametric studies of systems, complete systems, and it also computes the profitability of a, let's say, waste heat recovery applications for the end user. So in the end, you compute the cost per watt, the cost per watt hour, and then the number of years before the return on your investment, and then after that the profitability from the benefit of having this cheap electricity. So we can compute that, and then we are discussing with future customer. So I will show you a couple of applications. So we are only starting real life in situ applications with early adopters. And what you will see here is mainly directed towards waste heat recovery. Besides, some of the people here in the session are also working with us, and will test very soon our modules for IoT. But here I can show you basically mainly applications for thermoelectric generators on hot gas exhaust. So basically the two first applications are these applications. On the left, it's for a temperature of 400 degrees C. The second picture is on a waste burning site, and we are having hot gas exhaust of 190 degrees C. So this is a proof of concept, and we are now developing what you see on the right. So the last picture on the right, the idea is here to really extract the calories from the hot gas exhaust and have an external thermoelectric battery. We call this thermoelectric battery. Maybe it's a bad wording, but it's how we call it. So and we try to use as many as possible very standard elements that you could find in in other waste heat recovery technology to really minimize the cost. There's something that I wanted to say also to compare with, for instance, photovoltaic. You know, you see here on the right, you have a big gas exhaust pipe. In there, you have a small exchanger. Of course, we will maximize the exchange surface, but we capture only a fraction of the available heat. Okay, and then from the captured fraction, we convert a fraction. So the total, I would say, efficiency is very low. Okay, so we cannot say that the efficiencies are fantastic, but it's a low efficiency on a big quantity of heat, and in the end, it's at a very low cost. So that's a game changer. You can always retrieve this heat. So what we demonstrated is that the return on investment is very short, and it's very profitable. Okay, but if you compare to photovoltaic, of course, at the end of the year, you have maybe 4% because of the insulation rate and things like that. You have maybe 3-4% of global efficiency of photovoltaic over a year, but you capture only maybe 1/1,000,000th of the heat of the sun. So it's very low efficiency compared to the heat of the sun. So in this case, okay, with Thermoelectrics, we are capturing only a fraction of available heat, and we are converting only a fraction of this available heat. So what is our way forward? Now we want to achieve TRL 6-7 milestone for both big markets, I would say waste heat recovery and Internet of Things. We are implementing actually the manufacturing line, which means we will look for investors to buy, for instance, SPS machines, because we don't have our own at the moment. We subcontract this. And these TRL milestones will help us do the market validation. Of course, if we want to attract big investors, we need to validate the market on a number of examples. And I think I'm done. So if you want to contact me, here are my data, my email, my phone number. You can also reach out to Geoffrey if you are more familiar with him. And thank you for your attention.
Okay, thank you, Frederic. So we have time now for some discussion. So, Raul, I don't know if you want to read some of the questions that are there.
Yeah, maybe we should start from the top. right?
Yes, yes.
Raul,
Yes.
we'll start
Yes.
from the top.
Yes. So I think the next was for you also, Hao. This one. How, yes. Do you see Thermoelectrics R&D future as open source knowledge or IP protected development?
Very good question. So of course, R&D come at the cost, and so does IP. There's no point that we should hand over the IP to anybody. But the thing is, at the moment, there's no, how can I say, there's no strong engagement from industry. So I would be, how do I put it? It would be naive to wait and to see if the investors will come to buy our IP, because actually the players is in Thermoelectrics are startup companies like technology, like AEInnova, FlexiRamics, and thermal power. Sorry. So I mean, we're not going to buy any IPs before we earn our profits. So I think we need to take it as in a pragmatic way. So how do we lift the entire society while monetize our IP? So I don't have an answer here.
Thanks, Hao, for your answer. And next, another one that says, everyone, why even after decades of research in thermoelectrics, it is still far from wide commercial adoption? I think it's another question for you, Hao.
I think it's for everyone.
Yes,
It's a very good question. So I would say that because most of the research was driven from the scientific point of view, instead of driven from the market pool, right? There's a significant difference. Of course, I mean, from a scientific point of view, we need to understand the physical, the physics and the scientific origins of how the material works in order to discover and design more new materials. But from the market point of view, they are looking at different things, such as return of investment and the total cost of ownership. So from that point of view, we have significant lack of research that is oriented towards real application.
Thanks.
I can reinforce your message, Hao, and like you did in your company, you reached out to the industry, Bionic, in early stage, I would say, and we could see an interest directly. But even though everything takes time, we are 3 years now into development, and last year we launched the first serial real product. So again, it takes time. So a lesson learned, yeah, simply reach out to industry as soon as possible, as you can feel mature enough to reach out to the industry. That is my feeling.
Good point. I completely agree.
Sure. One from my colleague Vicente Pacheco from the Fraunhofer of Dresden. Raul, which role plays the price of the modules in the price of your devices? How much power do you need to supply with a TEG for our applications, for your application? So in our case, more or less, the price of the TEG is about 50, 60 euros, the TEG. The price of building, so the cost, the gross cost of production of these, just in materials, is about 250. So probably it's at 25% of the cost of the module. It is commonly sold by 450, 500 euros a device. But again, depending on the volume, it can affect the final margin. But yes, it's an important part of the cost. Okay. About the power generation, so it depends on mainly the sensor, also the data rate of the sensor. For example, for vibration monitoring, you commonly send data every 10, 5, 15 minutes because you are monitoring vibration equipments like motor, turbines, pumps, and you want to have a continuous monitoring of the process. If you need to send data quasi in real time, you are continuously burning energy, and this is why you need also, if your data must be processed or not processed, edge computing also applies again a new level of power consumption. Also, a type of sensor doesn't expend the same energy. A microphone, for example, that a vibration sensor, that a thermocouples. for example, for the thermocouple modules, that we monitor up to 8 temperature points of big furnaces. Thermocouples are power generators. So my sensor doesn't consume energy. In fact, generates energy. So it's a balance. From the perspective of energy, with just 25-30 degrees of delta T, we generate about more or less 50 milliwatts. And this is quite enough for sending data every 1-2 minutes in cadence. Also, it depends also in the chipset of wireless protocol you are using. It is the same, for example, LoRaWAN that consumes 20-30 milliwatts, that BLI that consumes 5 milliwatts, that narrowband IoT that could have peaks of up to 1 watt when it's connecting to the joining to the network. So again, depends on the application, on the communication, and the processing. But we can give better quality of service, absolutely, compared to a battery power sensor that commonly delivers data once every day, once every hour in the best case. Okay? Now this is for Ivana. So from Johannes de Boer. So what is the typical thermal specific resistance of the flexible ceramic in k watt per square meter?
Yeah, the cross direction, I think it was from Johannes, correct? So as a commercial person, I think in terms of conductivity and not resistance, I think they are connected, but I think you can better translate that. So we didn't focus much on that, and the answer is it depends, because it will also depend on what is the percentage of the fibers and which resin you use. But if you think what did we do until now, PI, the high, and BMI, epoxy, the highest was in BMI, but it was still below 1 in TC. As that's my honest answer, but we sure back to that open for collaboration. We can also discuss offline or in the mails and see if there is interest to work on something together. Yeah. Thanks.
Thank you. And another one for everyone. What temperature range do you think is most suitable for waste heat recovery? High temperature heat sources may offer high efficiency, but materials stability becomes a serious issue. Hey, Frederic?
Yeah, I have 2 points. First, I come back to the cost. Just one word on the cost. What I wanted to say, if is for us, for instance, it's an indication, but the materials themselves in our calculation is only 7% of the cost of the module. So labor is still, labor hours is still the major cost. And then if you take the cost breakdown per process, 90% of the cost is on sintering and dicing. So this is, but makes sense. Huh? And then on the temperature, so we have been discussing a lot with different potential customers for heat wave recovery. And most of the market is with quite degraded heat, so lower temperatures. I would say maybe 100, below 100. So I don't remember the exact figure, but if you go through the surveys from ADEM or from the EC publications, you will see that a lot of the heat is at low temperature. So that's where the competition is direct with bismuth telluride, and I think for these low temperatures, the magnesium-based thermoelectric materials are probably the best competitors for low temperatures. Just tell me if I'm wrong. Then if you go higher in temperatures, that's where you have different materials that can compete. Iron, vanadium, aluminum, despite a low efficiency, but interesting power factor is one of them, stable up to 400 degrees C. And then if you go to higher temperatures, tell me if I'm wrong, but you have silicon, germanium, things like that. So you have different materials from different range of temperature. The point is that the competition is not necessarily between the materials themselves, but competition with other existing technologies like ORCs, other technologies, which are very well installed you have like maybe 30, 35 competitors in ORCs with different ranges of powers. So it's difficult to compete with these. They are well established, but we can still, I think, compete with the low power ORCs because we have non-moving parts. We have less interference with process. But as Hao said, and I think many of you agree with that, is that this is a state of mindset change for the industry to really use this solution in their portfolio. So my 2 cents.
Thanks, Frederic.
If I may supplement on this, it's also related to Subra's question on high temperature. So what is most suitable for waste heat recovery? Indeed, when the temperature is high, let's say above 400, it's not waste heat anymore. There are a bunch of existing and reliable ways of using that heat. So we will not get it. Thermoelectrics cannot get it as a waste heat. And also, I would say there's no existing or reliable solution for thermoelectrics that works reliably long enough in that temperature range. If we have a high temperature source, that means in order to keep the delta T, we need to have cooling, active cooling on the backside, which is a strong break into our claim that thermoelectric is solid state. If we need to have running cooling water on the backside, the system is not solid state anymore. And that's the weak point of reliability, because no running water system will work in those industrial environment.
Okay. Yeah, maybe just one last aspect on that is that's why probably thermoelectric generators would be in good synergy with district heating and things like that, where like hot water is needed and we can preheat water. So that would be very convenient. I mean, we are looking at that, but of course, again, we need to find industrials okay to implement that.
Thanks, Hao and Frederic. A question for you, Hao. How high is maximum operation temperature of your flexible TEGs?
Well, the highest temperature is limited by first the substrates. Right now we're using polymers, so it's 250. If we switch to the FlexiRamics, I think it's a bit higher. And also the way that we bond the substrates with the materials. If you soldering, then it's 230. If you use welding, it can go up to 400. But again, it comes down to how the system, how robust is the system at this high temperature. So it's not only the modules, but the other electronics, which cannot tolerate that high temperature. So that really depends on the application. So right now we are limiting our upper limit to 200 degrees for most our products.
Okay, the question was answered. Yes, because we did make a question and Frederic answered. Let me see another more. Okay. And yes, one that is thanks for the presentation. A question for Ivana: what metallization options are available for flexible ceramics, and how does the cost compare your polymer flex and traditional rigid ceramics? Also, for the thicknesses shown, do you have any typical thermal resistance values? So
yeah, sure. Yeah, no, I understand. So the metallization options, I think it's not directly on ceramics what we did, but where Hao is there. So I think we tried copper or silver for now. On the composite that you also saw on the picture. So that is the PI composite. And I think it comes from 60 micron and then compressed to 30, something like that on the thickness. The cost, yeah, back to it depends. We are making we are on a pilot scale compared to everything ongoing today with the supply chain and materials comparable. Rising in prices, or even on a pilot scale, we can compare. Here you don't use much, and it is always back to, as already mentioned, a question of the total cost of ownership, but I would not necessarily because we are now busy with a new investment round for a higher or a broader scale of the production. So I actually, in looking with the other contacts and customers we have, the scale for us will actually be positive for the price. So I would not worry on that. But again, outside of this call, if I know what are we talking about, maybe I can already give the price today. And the last is again depending on the thicknesses. If we talk about the TC, it is on a XY, it is around it's 2.2 in 80 micron thickness in PI composite, and then 0.5 in Z. So, but yeah, back to we need to talk about always fiber loading versus resin when we talk about that direction. Yeah.
Okay.
I just want to supplement because I happen to know the cost of the metallization. Right now, we're using printing technology to print electrodes on the FlexiRamics. So because it's so thin and it's so scalable, so really the cost when we go to large production is negligible. The material cost is negligible. And the thermal resistance of FlexiRamics is between pure ceramic and pure polymer. That makes right, because the FlexiRamics is a mixture of pure ceramic, aluminum fiber, and polymer. So it's in between.
Okay, so I think we are really on time. I will give a special thanks to all the speakers here. Thanks for doing this webinar reliable, and I think all the people that has been joining with peaks of 90 people. I think I will also give a special thanks to all the attendees. You will have access to this webinar once we finalize tomorrow. We'll share to you the link, and also in our social media of all of us. That is in the invitation to join this session. You will see in our social media of LinkedIn also the video to see offline of this recording. So thanks for you. I give up a special thanks to all of you. Thanks for being so active, and I think we are doing this European thermoelectric community higher and higher, and we expect to have the cheaper and the biggest energy efficient thermal modules in the next 3-4 years to make the European sovereign in thermoelectric success. Thank you very much to all of you guys.
Thank you.
Thank
you very
you.
much.
Thank you.
Have a nice day.
Thank you.
Ciao, ciao.
Bye-bye.
Thank you.
Thank you to all of you.
Bye.
Thank you.